Today we study current and resistance. An electric current I in a conductor is defined by dq over dt, time derivative of charge. Consider inside this wire, there is a cross-sectional area A, and current is for the charge dq penetrating the cross-sectional area of a wire inside the circuit per unit time. Okay, so current I is dq over dt, time derivative of charge that passes through a cross-sectional area of A, where dq is the amount of charge passing a point. In some case, this wire has negligible cross-sectional area. We cut at some point and dq passes this point. Delta q passes this point during the time delta t. Then we say this is current I. The direction of the electric current is taken as the direction along which positive charge carriers move. In fact, in most cases, the charge carriers are electrons, and the electron has a negative charge. However, historically, we have determined the sign of the charge carrier by positive one. So the actual direction of the flow of charge carrier that are mostly electrons is opposite to the direction of the current. So unfortunately, we use positive charge carriers motion to determine the direction of the electric current. Normally, only conduction electrons that are negatively charged can move. Okay, conduction electrons, that electron has a negative charge. So this is opposite to the direction of current. The free electrons, so-called conduction electrons, in an isolated length of copper wire are in random motion at speeds of order 10 to the 6 meter per second. They are very, very fast. However, in fact, their directions of motion are randomly distributed, so as long as there is no potential difference between the two terminals of this wire, there is no actual current. In most cases, the motion of conduction electrons are randomly distributed, so average current vanishes unless there is some application of the EMF. The charge passing a cross-sectional area during the time interval 0 to t can be computed by integration. If the current varies depending on time, then the current, the amount of charge that passes the cross-sectional area, amount of charge delta q can be evaluated by integrating differential amount of electric charge, that is I dt. Because of this, dq equals I dt. The current is the same in any cross-section of a conducting wire. That means the charge is not accumulated at a certain point. In fact, charge can be accumulated to a certain point if there is a capacitor C, and if there is a current flowing in, then the charge will be accumulated, and negative charge will be accumulated in the opposite, and current I flows into the left and flows out. So current I is flowing. This side is a positively charged and this side is negatively charged in the case of capacitor. However, in a resistor or wire, we assume that there is no accumulation of charge, so current flows continuously, and at any point the current should be the same because of the conservation of electric charge. The SI unit for current is the coulomb per second. Coulomb is the SI unit of charge. Second is the SI unit of time. So the SI unit of current is coulomb per second, and it is written in the form ampere. The conservation of charge and no accumulation of charge inside the wire or resistor states that there is a conservation of current. Conservation of current is a consequence of conservation of charge. Suppose that I1 through In are flowing into a junction. There is a junction and wire segment. There's current comes in I1, I2, I3, and so on. In minus 1, In. Currents are coming in. Then the sum of all of the currents coming in should be, if I1 prime is coming out, I2 prime, I3 prime, and In prime. This is the current flowing into a junction, and these are the currents flowing out of that junction. This coming in must be the same as coming out. So the charge is not accumulated anywhere. So the current charge conservation restricts the conservation of current. The current arrow is drawn in the direction of motion for positive charge carriers, not electrons. Even if the actual charge carriers are negative, that move in opposite direction. A car battery rated at 80 ampere hour, this is time, and ampere, the time is hour, and ampere is a current. So current times time is the charge, amount of charge. An ampere hour is a unit of charge, right? That is not the same as coulomb, because 1 coulomb is 1 ampere times 1 second. Current is a measure of the amount of charge that moves past a point per unit time. Charge time. Current in a conductor is normally due to the drift motion of the conduction electrons due to the electric fields. These conduction electrons are distributed, randomly distributed inside wire, and they are mostly moving random motion. However, as soon as the electric field is applied, so this is a positive, this is negative, the actual electron, conduction electron, moves along this direction, opposite to the electric field. As soon as the external electric field is applied. Okay? So electrons are moving to the left, and the current I is flowing to the right. This figure shows a junction at which I0 flows in, and two currents, I1 and I2, flow out. The current satisfy conservation of current states that incoming current is I0, sum of outgoing currents is I1 plus I2. Next, we consider the current density. Current I is related to the current density J. You remember electric field flux phi was evaluated by integrating electric field over a surface by considering the scalar product with the differential area element over a surface. It is just like that. So what we do is just to replace the electric field flux phi with the current, and the electric field with current density J, and area is kept the same. So if the current density is constant, then and this area, cross-sectional area of the surface, is parallel to J, then J can be delta Q over delta T, that is the current I, and delta A. So current density means the amount of current passing through the cross-sectional area per unit time per unit area. Okay. In addition, there is a scalar product, just like the case of electric field flux case. It depends on the direction. The cosine theta, where theta is the angle between the current density and the area vector. The differential area vector element, dA, is a vector perpendicular to a surface element of the area dA, and integral is taken over any surface S cutting across the conductor. Hence, the surface dA is in this direction, and current density J is in this direction, and they make right angle. Then we would have current I, J dot dA, over the surface, and because they are making right angle, this current is 0. In case dA is heading to the right and J is parallel, then we would say the current I is j dot dA, and because they are parallel, this is just j times A, in case j is constant all over the surface. In general, they make angle theta, so j dot dA equals j dA cosine theta. The relation between I and J is analogous to that between electric flux phi and the electric field E. We have explained already. Current I is a scalar. Right, this is a scalar product. So current I is a scalar. Current density J is a vector. Yes, J is a vector, dA is a vector, and we compute the scalar product between the current density and differential area element vector. If J is uniform on S, then just like what I have explained already, J dot A will be the value. If J is paired to dA, then dI is JdA, and I can be computed by integrating dI, and dI is J dot dA. Okay. J is anti-parallel, then opposite cosine theta becomes -1, so dI is minus J dA. If J is perpendicular to dA, then the current element will be vanishing because cosine theta becomes 0. A flow of charges, a volume charge density. Volume charge density means volume per unit volume. Okay? Is moving with the velocity v. Okay. There's a uniform charge distributed over this space, and this body, charged body, has a cross-sectional area A, and this one is moving with the velocity v. Then during the time delta t, one face of this volume go ahead with the displacement v delta d. And we find there are total number of charged particle inside this volume spanned by swiped by the surface during the time delta t can be computed as delta n is the number of particles, and if this is electric charge is E, then amount of charge delta Q contained inside this volume will be delta N times single charge. So delta Q is E times delta N. What about the volume of this space? Okay, V delta T, that is the displacement, and this is the area A. So scalar area is A, and vector area is A multiplied by A. Surface area A multiplied by the unit vector normal to the surface, right? And we assume that V is parallel to this normal vector. Then the volume of this parallel pipe will be A dot V delta T. So, as we have defined, the charge density is rho is delta Q over delta V, and substitute this one and this one, E delta N, and delta V is A dot V scalar product delta T. This will be the charge density. Or delta Q, amount of charge contained in this space, is density times volume. Right. Number of charge carriers, delta N, should be charge divided by the amount of charge per single charge carrier. And this charge is expressed as a density times volume divided by single charge. Okay. Now this volume is substituted in here. So delta N, number of charges, will be rho delta V A dot V delta T single charge. We now define the number density. Number density means how many particles are there in a unit volume. The number density N is number divided by volume. Therefore, delta N, the number of charge carrier contained in the space, is number density times volume. Just like delta Q is charge density times volume. Now we replace this volume with A dot V delta T, and amount of charge inside that volume is elementary charge times number of particles, and elementary charge is there. Number of particles is a product of number density and volume, and then substitute this result, volume A dot V delta T. Alright, so delta Q equals N E A dot V delta T. We divide both sides by delta T, then we have delta Q over delta T, that is current, N E V A. We remember the current I is an integral of current density dA. Because in this case, dA integral can be expressed as A, because the current density J is uniform, then we find that dot A. Therefore, this one should be the current density. So current density is NEV. Okay? NE. N equals delta N over delta V. And NE equals E delta N over delta V. And E delta N is actually the charge, delta Q over delta V. So, charge per unit volume is rho Therefore, say J equals rho V. Rho delta Q over delta V. Okay? An electric field E is established in a conductor. In an electrostatic case, the electric field must vanish inside the conductor. That's right. If the external electric field is applied to a conductor, then charge carriers accelerate. It is impossible to make an equilibrium because of the external force, so they are forced to move forward. Positive charge carriers accelerate parallel to E. Negative charge carriers accelerate anti-parallel to electric field. Accelerated charged carriers are slowed down because of random collisions with other charged particles inside the conductor. The charged carriers acquire drift speed Vd in the direction of E. So, charged carriers are randomly distributed and they usually move in random direction, but after applying the external electric field, negative charge carriers, they tend to accelerate opposite to the electric field. But actually, they do not accelerate forever because they make a collision with another atoms, because the atom nucleus has charges positively charged and the negative charge is distribution due to the another electrons. So they can never accelerate forever. However, due to the external electric field, they accelerate and they make a collision and become their directions abandoned, and then they accelerate again, and so on. So if we average over time, it looks like they are flowing continuously with a constant speed, and that after averaging out with respect to time, we say the resultant velocity of each charged carrier is denoted by the drift velocity Vd. So, case electrons is there, negative charged particles is charged carrier. Wait a second. All right. Arts and science buildings under construction. Okay. So charged carriers are negatively charged, and if there is an external electric field applied, then the charged carrier will be accelerated opposite to the direction of the external electric field. the resultant average velocity of the charged carrier is to be expressed as a drift velocity Vd. The resistance and resistivity. Resistance is defined by this Ohm's law formula. This one states that if there is a potential difference between two terminals of a resistor, or potential V is there, then the current passing through this resistor, current I, is proportional to the potential difference. And that proportionality constant is the resistance R. So V equals IR. So current I is proportional to the potential difference between the two terminals of a resistor. The SI unit of the resistance is resistor is a circuit element, physical element, and resistance is this constant, proportionality constant, the SI unit for this resistance is called ohm, and symbol is omega. We do not read it omega, but it is ohm. And according to this relation, R equals V over I, and if we substitute SI unit for the potential difference, it is volt, 1 volt, and current I, SI unit of the current is ampere, so volt per ampere is identical to the ohm. As a circuit unit, a resistor is a conductor which provides a specified resistance R. Okay. The resistance depends both on material and geometry of a resistor. So geometry means the shape of the material. However, resistivity rho depends only on the material. It doesn't matter whether it is a flat or a kind of lump. Resistivity is independent of geometry of a resistor. So resistance is a property of an object. Resistivity is a property of a material. So because object has some shape, and so resistance depends on the shape of an object as well as the material. Resistivity rho and conductivity sigma, they are closely related. They are reciprocal, mutually reciprocal. And keep in mind that they are mutually reciprocal. The J current density equals sigma E. Or E equals rho J. Memorize current density, sigma E, and electric field, and rho J, where J is the current density. If we combine the SI units of electric field and current density, then we obtain the unit of rho, the ohm meter. Okay. The electric field E and current density J are related to the resistivity as electric field E equals rho J. The SI unit of the conductivity, sigma, is conductivity. conductivity. Rho is resistivity. If we know the resistivity of a substance such as copper, we can calculate the resistance of a length of wire made of that substance. Consider wire of cross-sectional area A, length L, cross-sectional area A, and length L, applied with the potential difference V. The electric field is minus and plus. So this V equals 0. V, there is electric field, and there is a uniform electric field. So electric field is potential difference divided by distance, right? Current density. Current density is current divided by cross-sectional area A. According to the definition of resistivity, resistivity is defined by electric field divided by current density. And electric field, we copy this formula in here. Electric field is potential difference divided by distance L. Current density is current divided by area. And we apply I. V over R. I equals V over R. Substitute V over R. The VV cancels. L is here in the denominator. A is in the numerator. And R numerator. So resistance R can be computed rho resistivity times L divided by area. So resistance of a conducting wire of length L and cross-sectional area, and resistivity rho, then R can be computed in this way. The resistance is proportional to the length, and is reciprocally proportional to the cross-sectional area. This formula can be applied to solve these problems. In addition, you can train yourself with this formula by solving the following problems. Next, we consider Ohm's law. This I, the V over R, is the Ohm's law. V equals IR. A conducting device obeys Ohm's law when the resistance is independent of the magnitude and polarity of the applied potential difference. A conducting material obeys Ohm's law when resistivity of the material is independent of magnitude and direction of the applied electric field. This is the explanation of the drift velocity. please read it through, and there are enough explanation. But basically, the charge carriers are randomly distributed, and as soon as we apply the external electric field, the charge carriers will be accelerated, but they can never accelerate forever. Instead, they hit other particles and becomes almost at rest and then accelerate again, and repeated acceleration makes the average value for the drift velocity of the charge carrier. And this is a microscopic explanation, but this is not exactly true, but this gives a schematic view. Here, mean free time, tau, means it is accelerating for a while, and then it hit the other particle and becomes at rest, and then accelerate again. Repeated acceleration does not make the current increasing as time goes on. For example, if you, for an object in free space, it will accelerate forever. So with under constant gravitational field, the velocity increases as time goes on. So this is not the case. It accelerates for a short time and it hit something and then stop and accelerate again, stop, accelerate again. So this drift velocity is average velocity of the charge carriers. Next, we consider power. Power is work per unit time. Power. The potential of a charge dq changes by V. Then what happens? Potential energy. Potential. Amount of charge that has shifted its own potential. Right? Potential energy shift can be expressed like that. And then dq is current I times dt. So if we substitute dq with I dt, then potential energy shift will be IV times dt. The potential energy is IV. Okay? So this is the power, work per unit time. Electric power of a resistor. So this is a positive value, but that positive value means the resistor consumes energy loss. And this energy loss is IV, and according to Ohm's law, V equals IR. Substitute IR in here, there's IR, so it is I squared R. Or I equals V over R, substitute in here, then square R, so V squared over R. Alright, so it can be expressed in either I square R or V squared over R. The SI unit of power is I times I, current, times V, volt ampere. Now 1 volt can be expressed in joule per coulomb. Coulomb, amperes, coulomb per second, coulomb cancels, joule per second, that is watt. So volt ampere is watt. This is an interesting explanation. why we use a very high potential when we send the electricity from the power plant to our home. There are semiconductors and superconductors. Semiconductors sometimes just let us read it through. Semiconductors are materials that have few conduction electrons but can become conductors when they are doped with other atoms that contribute to charge carriers. So sometimes it allows current, but sometimes not. That means there is a polarity. If you apply plus and minus, then the current flows, and apply minus plus, then does not flow. So in this case, a conductor, insulator, so case by case, there's a polarity. Then it is called semiconductor. And superconductors, the case R goes to 0. Materials that lose all electrical resistance at low temperatures. Some materials that superconduct at surprisingly high temperatures, in the room temperatures, then it is very useful. Compared to the conductor, semiconductor has a negative temperature coefficient of resistivity, but it is too advanced one. In the remaining part of this class, we just review mathematics that are quite useful in our future calculations. First, elementary concept of matrix. M by N matrix, there are list of numbers. We say these are the rows. First row, second row. These are the columns. And if the number of rows and number of columns are the same, then it's a square matrix. And the subscript, Aij, this one means ith row, jth column. And elements of a matrix, entry or element, they are in general complex, and sometimes we use real, sometimes we use complex numbers. Here, I and j represent the row and column indices. Matrix operations. Matrix 1, 2, 3, 4 plus A, B, C, D. Then sum of these two matrices, 1 plus A, 2 plus B, 3 plus C, 4 plus rho 4 plus D, B, C. Okay. We can add two matrices if the size, number of rows, number of columns are the same, then we can add them. Scalar multiplication, we can multiply some number, A, 1, 2, 3, 4, then A, 2A, 3A, 4A. Okay? Transpose. Transpose, we have A, B, C, D. Of transpose is keep the diagonal piece. This is diagonal. Keep the diagonal of diagonal one opposite direction. Upside down. B, C. This is transpose. Hermitian conjugate. This one is transpose and complex conjugate. So transpose A, D, C, E, and complex conjugate. This is Hermitian conjugate. Multiplication. A, B, C, D, X, Y. We can multiply two matrices, this row and column. Okay, here A, row, column, connect, multiply, and then add. So AX, BY, and add. Multiply CX, DY, and this is matrix multiplication. So A, B, C, D, 1, 2, 3, 4. That's that. 1, 3. A plus the 3B, C plus the 3D, 2A plus the 4B, 2C plus the 4D. So matrix multiplication can be done like that. But matrix multiplication is not commutative. So AB matrix product is not always equal to BA. There are special matrices, very simple matrices. Identity matrix. Identity matrix, all diagonal components are all equal to 0, except that everything is a 0. We use Kronecker delta to represent the elements of identity matrix. Identity matrix is actually delta ij. That means delta ij equals either 1 or 0. If I equals j, it is 1. Row index and column index are the same. Then it is 1. But if the index of row and column are different, it is always 0. So this is Kronecker delta. If the number of columns is identical to that of rows, then the matrix is called the square matrix. I already explained. For an n by n square matrix A, there exists n by n matrix B such that product is identity. Then we call this B equals A inverse, or A is B inverse. Okay? N by n square matrix A. Trace A, B, C, D. Trace. Trace is the sum of the diagonal elements. Trace is the sum of diagonal elements. If A, B, C, D, for example, 1, 2, 3, 4, transpose equals 1, 4, 3, 2. This is not equal to 1, 2, 3, 4, right? In general, transpose is not the same as the original matrix. However, 1, 2, 2, 1. Transpose. Transpose is the same as the original one. In that case, we say symmetric matrix. There's orthogonal matrix. And sometimes transpose equals inverse. That is orthogonal matrix. A special orthogonal matrix is cosine theta, sine theta, minus sine theta. This is the rotation matrix on the two-dimensional plane, and actually our transpose is our inverse. This is a special case, and this is orthogonal matrix. Sometimes transpose and complex conjugate is inverse. A very interesting thing. There is a unitary matrix. Sometimes transpose complex conjugate, that is Hermitian conjugate. Hermitian conjugate is itself, then we call this Hermitian matrix. Kronecker delta, we already explained the Kronecker delta. Einstein notation or Einstein summation conventions. If there are too many indices, we do not display the summation notation. If there is a repeated indices, repeated II, JJ, then they are related to matrix multiplication. And usually, if we employ the Einstein notation for summation convention, then the repeated indices are assumed to be summed over I equals 1 through 3. We have studied I hat, J hat, and K hat. They are the unit vectors along the x-axis, y-axis, and z-axis. And sometimes it is convenient to express I as E1, J as E2, and K as E3, and X as X1, Y as X2, Z as X3. Then the computation becomes greatly simplified. For example, if we want to write down the scalar product, II equals 1, JJ 1, KK scalar product 1. But it can simply be expressed EI, that EJ, EI equals 1, or I equals 1, 2, or 3. So we can simplify the expression. For example, EI dot EJ equals 0 if I is not equal to J. This one can be expressed as I dot J, J dot K, K dot I equals 0. But we can simply write it EI dot EJ equals delta IJ. Why? If they are the same, it is 1. If they are different, it is 0. So EI dot EJ equals delta IJ. Very, very simply explained. Okay, Kronecker delta satisfy the following identities. Delta IJ, delta IJ. That is actually the sum over I equals 1 to 3, sum over I equals 1 to 3, delta IJ, delta JI. Actually, delta IJ is a symmetric matrix. You know, this is IJJI. This is a matrix, identity matrix product II. Sum of Y. And product of identity matrix is like that. Identity matrix II, that is trace. Trace of identity matrix. Trace of identity matrix is 1 plus 1 plus 1 equals 3. We use n for n times n matrix, n by n matrix, but for 3 by 3 matrix, it's just a 3. Now let us consider triple Levi-Civita tensor epsilon ijk. That is defined by the triple scalar product. We know that I cross J dot K. This is triple scalar product. This style scalar product becomes non-vanishing only if all these three elements are all orthogonal to among one another, right? So we have to choose X, Y, and Z. X, Y, and Z component. There's something wrong. X, Y, and Z component one by one. That means, for example, E1 cross E2 dot E3. That's fine. However, if any two of them are the same, for example, E1 cross E1 dot E3 is 0. That means they are either 0 when I, J, K, a set is not equal to 1, 2, 3. So this means any two of them are the same. Then epsilon ijk vanishes. It is non-vanishing only if the three elements are different. That means they construct a permutation. There are 6 permutations. We list the 3 different numbers in a row. I have 3 cases. So you can put 1, 2, or 3. Once you choose one element, for example 1, then you can put the number 203. So you have only two choices left. You have made use two numbers. At the end, you have only a single choice. Therefore, this is 3 factorial. That 3 factorial is a 3 distinct permutations. Among 6 permutations, there are 3 permutations. They are even permutations. That means this triple scalar product has a positive value, plus 1. There are 3 other cases among 6 permutations. They are called odd permutations. Odd permutations can be obtained by exchanging any two elements in even permutation. So the triple scalar product for odd permutation is always negative value. In summary, Levi-Civita tensor is not vanishing, only first these are 6 cases. This is 1, 2, 3, 2, 3, 1, 3, 1, 2, cycling. 2, 1, 3, that is exchanging 2 and 1. 2, 3, 1 here. 1, 3, 2. 3, 2, 1, they are the negative. This is positive. So this is even permutation, odd permutation. Because of the cross product in the triple scalar product, cross product is anti-symmetric on the exchange of two vectors, while the scalar product is symmetric on the exchange of two vectors. The Levi-Civita tensor is completely anti-symmetric on the exchange of any two indices. For example, 1, 2, 3 is 1. 2, 1, 3, we have exchanged any two. Exchanging by 1, you flip the side by -1. Alright. This part is rather difficult for you to understand. So any student who are interested in learning the permutation theory, just follow up the calculation, because I have explained everything in it. This permutation calculation is very, very important to compute the determinant. And actually, the triple scalar product can be expressed as a determinant. The determinant is defined by for n by n square matrix. Especially we are interested in the 3 by 3 case. We are mostly working on the 3-dimensional Euclidean space. We list up the 3 vectors in a row, and actually this can be a triple scalar product. For example, A cross B times C, that is expressed as AX, AY, AZ, BX, BY, BZ, CX, CY, CZ. So this is the determinant. What is the determinant? This triple scalar product. Hey, in here we find the Levi-Civita tensor we just have explained. Please follow the calculations. I believe you must be acquainted with the determinant calculation because you have already taken the mathematics class. All right. There are useful identities for the determinant of product of matrix is the product of the determinants. Because of that, if it is A times A inverse, that is identity, we have the determinant of identity is determinant of 1, 1, 1, 1, 1. So the answer is 1 times 1, 1, 1, 1, 1. That is 1. Identity matrix has the determinant identity. Therefore, the inverse matrix has the determinant that is reciprocal to the determinant of A. Triple scalar product was expressed in terms of a determinant of a square matrix whose rows, either rows or columns, are the components of the three vectors. That can also be used for computing the cross product of the two vectors by replacing the first row with the unit vectors. The Leibniz-Civita tensor calculation can be applied to derive the back cap rule that is very useful in physics calculation as well as in mathematics calculation. Back cap rule is A cross B cross C. Triple vector product is back minus cap C A B. You must be careful not to use this calculation. This one is different from, this is different from that one. You can replace this one as a minus A cross B. And then you can apply the back cap rule to this expression. Be careful. All right. So today we have studied the current and resistance. The current in a wire, conducting wire, flows when there's an external electric field is applied. And a conductor that is not an ideal conductor but has some resistance is following the rule for the proportionality between the current and applied potential difference between the two terminals of an object. That is called the Ohm's law. And this is how to compute the current. And we have introduced the current density. It's just like the electric field flux computation. Current density is integrated over a surface to find out the current. And then we studied resistivity and conductivity. And by making use of these Ohm's law, we were able to find the resistance of a resistor of a specific geometry. In a microscopic point of view, applied electric field accelerates the conducting electrons, but they cannot They cannot accelerate forever. They hit the other particles and stops, and the acceleration is